So let me start. Sorry, just to set up a few things before I begin. Hello, everyone. My name is Matlekovic. I am doing a PhD in computer science here in Denmark at Department of Mathematics and Computer Science, the University of Southern Denmark. And I'm doing research in autonomous UAVs mission planning. But my background is actually in electrical engineering and IT, and I specialized in robotics control. I just started my PhD recently, and actually this is the first time that I'm presenting at a conference, so I'm very excited for this opportunity. And I hope you will find my research as interesting as much as I do. Peter Schneider-Kamp, he is my PhD supervisor, and he is a professor here at the Department of Mathematics and Computer Science. And his research is mostly focused in AI and also mission planning for autonomous drones. So in this work, we present the process for migration of application for infrastructure inspection, actually for mission planning using autonomous drones, and migration from monolithic architecture to microservices. So I would like to start with the big picture and tell you a little bit about the project we are participating, and this research is actually part of that project. So about infrastructure inspection, there are some conventional ways how it is being done right now. Usually construction workers are either climbing power towers, bridges, or they are employing some heavy machinery, as you can see on this third picture, for inspecting bridges, or either using helicopters, or just visually walking through, for example, railways, and inspecting it for damages. What is actually here in with this conventional inspection? It is a little bit dangerous for construction workers, and some previous research shown that falls from inspection sites are leading cause of death among construction workers. It can also be expensive, like employing this heavy machinery or using helicopters, fueling helicopters. So it would be good to have like some alternative ways for inspecting the infrastructure. And then in recent years, more and more autonomous systems are being employed for infrastructure inspections, like to save costs and eliminate risks, like, for example, flying drones or crawling robots for inspecting power lines and bridges. For this project, this project is about autonomous infrastructure inspection using drones. But what is special about the project is that the drones are continuously operating, and the idea is that they would inspect the power towers, power lines, and hook on the power line to charge when they need charging, and just continue operating after they are charged. Actually, before applying for this project, we are working with partners from industry and academia, and we've done some research which showed that in Denmark only, most of the bridges are in a proximity of the power lines, which means that we can charge the drones on the power lines, and go to inspect the bridge if it's close to the power line. So basically that's the idea for inspection. Also the drones could have artificial intelligence on board for automatic detection of damages on the structures. The part that we are doing here in the project is developing the cloud platform for mission planning monitoring. So the preliminary system design looks something like this. So we would expect to have some kind of web interface for inspection operators to be able to plan the inspection mission, to send to the drones instructions on where to fly, what to inspect, what are the inspection targets, and monitor on the interface how the inspection progress is going, and also store all the data received from the drones, like images or videos, detected damages. We would build a cloud platform and store it there in a database. Then after, we can analyze the inspection data also using that cloud platform. So this system design consists of three levels, let's say. One is a cloud platform for mission management, and then drones running the drone robot operating system, and a network for communication between the cloud and the drones. And today I'm going to talk about the cloud platform. So these are some objectives we identified that we would like that cloud platform to have. For example, we want to easily upgrade the platform, because first, when we start developing, we expect that the platform will grow in features, that we will want to add like some more analytics features, maybe include some higher intelligence, let's say, like take into account weathers, retrieve different data from open sources, and plan the routes as optimal as possible. Then we also want to be able to, when we have, since this is the research project and we don't have developers constantly working on this, so we are always like changing. We want for the platform to be able to be easily understandable, so that the developers don't have to spend time understanding the code base, so they can get on board really fast and start developing a new feature in the cloud. Also, we would like to prepare the platform for the future and provide optimal or near optimal route calculation, even for a high number of concurrent users, meaning that if we want to share this platform with inspection operators, we would expect that the platform will be used by many people at the same time, calculating different inspection missions. So we want the platform to support many users and not to get clogged, let's say. And also, we want to reduce the time from feature development to deployment. So we want to make that time as short as possible. So when we develop a new feature, we want to get it to the production as soon as possible, so that everybody can use it after. So first we started with LiMiC. Actually, it was developed before I started my PhD. And LiMiC is a linear infrastructure mission control web app. And it's exactly what I described previously. So it's a global inspection, mission planning, and scheduling app. It is developed in a monolithic architecture. meaning that there was actually no any kind of organization of the code. It was just like naturally developing with all the features in the same code base, and the application provided calculations for near optimal routes for UAVs to inspect power towers and power lines. Front end was a map-based web interface where the user could choose or select the inspection targets on the map and calculate routes for the chosen number of drones to inspect those targets, or to plan the high-level paths to reach the targets. For backend, the application was actually building a graph from power tower locations and calculating shortest paths based on A-star algorithm, and scheduling the order, basically solving the vehicle routing problem, scheduling the order of visiting for many drones to visit many chosen targets based on this calculated shortest path. And application was developed, deployed to the cloud. If you are interested in more details for how this algorithm for route calculation works, there has been a paper published previously with more details and with more description of the exact algorithm. And here we are focusing on architecture. So just to show you how it looks when it's exposed to the internet. So orange dots represent drones, and we can choose how many of these drones are going to the inspection. And then we select the targets, which are green dots here. And after we press calculate route, we got this calculation, which is visualized on the web interface. The idea after that is to send waypoints to the drones for navigation to the targets. But after the application was first developed, we realized that it is really difficult to add new features, because even I also spend a lot of time just to understand the code base and where is what. It was very disorganized, I would say. So we wanted to speed up the development of new features, because with monolithic architecture, it was not that easy. Also, the application was deployed manually, meaning that every time that different developers contribute to the application, they would have to deploy it on their own, or it would impose a lot of difficulties for collaboration between the developers, because they would not be aware of what other people deployed. Also, the application provided no risk diversification, meaning that any fallacy in just one part of the system will bring the whole system down, and nothing would work. We would not be able to see the web interface and calculate routes. Also, we realized that for many, if we select, if we send a lot of drones, if we are trying to calculate a lot of routes, sending many drones to the inspection of many towers, that processing time for route calculation grows exponentially with increasing number of sources and targets, with sources being drone locations and targets being selected infrastructure for inspection. And also, we were not able to scale the application. We would not be able to target specific parts of the system, which we know that they have a heavier load, and we would not be able to scale just this part. So if we wanted to scale application to support many concurrent users, we would have to deploy the application multiple times, even the parts that are not under the high demand. So our proposed solution was to migrate the application to microservices. Microservices are a collection of small loosely coupled services. They have independent boundaries between them. Each service has its own dependencies, and that way they are easy to maintain if we compare it with Monolith and if they are structured in a good way. This provides a better navigation through the code base because the developers, they don't have to be concerned with the code inside the service. They just need to know what the purpose of each service is, and they have exposed endpoints or APIs where they can just use that service, retrieve the data, or make a request to that service. Also, for better collaboration between developers, we used GitLab, which is a DevOps tool made for collaboration and for integration with, for example, Kubernetes cluster. Kubernetes is a good way to deploy microservices because it enables very easy and independent scaling of services. So when we realize that we have a higher demand for some services and some other services we just have to use once or make just a one request, then we would like the services with high demand, we would like to scale them, like to multiply, to have more replicas and to use that ones. For isolation of microservices, we proposed Docker containers. And here we describe the process of migration from Monolith to microservices in 3 steps. First one was identification. We had to first recognize all the processes in our monolithic applications and all the dependencies these processes have, and then separate them into independent standalone units, which is the second part, isolation. After we made these 2 steps, identification and isolation, we want to implement the microservices isolated within a framework enabling communication in between. So during the identification and isolation process, we realized, okay, that we have a web interface, and then first process was extraction of the location data about the infrastructure from open sources, for example, railways, where are exactly the railways, and then where the power towers are located, power lines, and bridges. After we extracted the data, another process was to build a graph from extracted data, because then on the graph we can search for shortest paths and schedule near optimal order of drones visiting the infrastructure targets. Yes, for example, here it's important to mention that, for example, graph building, it is triggered only when new locations are added, new bridges, new towers, which doesn't happen very often. It's not that they build a new bridge every day. So this is not a service, this is not something where we would expect a high demand. But on the other side, calculation of shortest paths is used like really heavily because every time we chose towers, it is calculating all the options to find the shortest path, and then scheduling is determining the order, looking for the shortest paths, and determining which drone will actually fly to which selected tower. So we decided to separate it like this and implement it in microservices. So here we have railways, towers, and bridges, 3 different services, which are extracting these infrastructure locations from OpenStreetMap's open source data, saving it to the database, and serving it to the graph service or to the web interface for visualization on the interface. We used a fast API framework for exposing APIs or endpoints. So if we want to request tower locations, we would create a request to tower service to retrieve the data. And one other thing is that we want to keep the drones flying around the infrastructure because we expect that it will be a bit difficult to get regulators regulation permissions for just random flight with the drones. So we expect that if we keep the drones near the infrastructure, it will be easier from a regulatory point of view. The data is stored in a Mongo database. It's a NoSQL database. It seemed as a simplest solution because we don't need to query this data very often, and it is easy to query, and it also provides querying by geolocation. For graph building, we use NetworkX library, and we build nodes from the locations and then edges representing the distances between these nodes. Then A-star Pathfinder service. So every time a user creates a request to vehicle routing service, vehicle routing will take all the sources and all the targets and send many requests to the A-star Pathfinder. Actually, it will send the requests for each combination of source and target to the A-star Pathfinder. And the A-star Pathfinder will return the shortest path for each combination. And then VRP will look at the distance matrix created from these shortest paths and determine the near optimal order of visiting, or based on the shortest paths for each combination, it will decide which drone would be the best to go to inspect which power tower. And for VRP, we used Google OR tools. Maybe it is important also to say that VRP is making requests to A-star Pathfinder asynchronously because it speeds up the calculation significantly. For deployment, we chose to deploy to small Minikube Kubernetes cluster. It is a one node cluster. Usually Kubernetes cluster can have multiple nodes with benefits being, if, for example, one node fails, the system is still running. But this, as a proof of concept, it was enough for our use case to just test the processing time between the monolith and microservices. We also integrated the cluster within GitLab. So, for example, when the developer pushes some new changes into the code, it will trigger automatic building of the Docker containers, because each service contains a Docker file, and it will build the image, and it will be deployed to the Kubernetes cluster, where each service is running in a pod. And then these pods can be replicated. For example, if we want many replicas of A-star pods, we will just put in a configuration files how many do we want, or we can just set up an automatic scaling, which will scale the services based on the demand for this service. After the services are deployed, we implemented very simple testing just to test if the route calculation is working as we would expect. And in the end, we compared the performance between the monolithic application and the newly developed microservices. We containerize the monolith and deploy it to the same Minikube cluster just to assure that running environments are the same. And we developed a test case consisting of a different number of sources, which are UAVs locations and targets tower locations. Then we used some different combinations for number of sources and number of targets, where we increased the number of sources exponentially from 1 to 16 and targets from 1 to 64, and generated 100 random requests for each combination. So in total, 3,500 requests. We tested the monolithic system, and then we tested the microservices system with just one of each pods deployed, so without scaling. But then we also scaled A-star pod, because we know that this is the heaviest calculations are happening right here. And then we try to scale it. So we deployed 10 A-star pod replicas to see how it will affect the performance. So this is the first graph showing how the monolithic system processing time exponentially increased for different numbers of targets. So this graph is showing just one drone and calculation for example, 1, 2, 4, 8, 16, 32, and 60 for number of targets. So in monolithic version, it took almost 3 hours to calculate for one drone to inspect pets, to calculate pets, for one drone to inspect 60 for targets. And then we increased number of drones, and the graph was not changing drastically, but it was changing. So for increasing number of sources, for 8 sources, for 16 sources, we can see how monolith is performing slower even from the beginning. But for low number of sources, the difference is not high. Even sometimes microservices performs slower. There is a reason for that also. You can see it better here, where we also visualized the other way around, just to emphasize what is happening with microservice version. Where here we are just changing the number of sources or number of drones for inspecting just one target, and we can see that microservices perform much slower than monolith. That is because of the overhead of the communication between the services and load balancing. So in monolith we don't have this message passing between the services. And for low number of targets, microservices were slower because of that. But then when we increase the number of targets, here you can already see that if we have a 10 A-star pod deployments, it is performing faster than monolith. But with just one pod deployment, it is still slower. So here you can see for 4 targets, and then the difference is increasing. This is the final graph for 66 for inspection of 64 different towers. To conclude, in the end, we showed that migrating to microservices actually impacted the route calculation performance, and it is faster with microservices. Although for low number of sources and target, Monolith performed faster because of this overhead of communication. But when we increase the number of A-star pod replicas, microservices outperformed Monolith. These are in general some benefits we got from migrating from Monolith to microservices, not only faster route calculation, but we have continuous integration and deployment, which is speeding up the development and enabling faster development and better collaboration. It is easier to add new features because it doesn't require a lot of time spending to understand the code base. And we saved a lot of cloud resources because we don't have to scale all the Monolith to increase the support for concurrent users. We can just scale the services with high demand. And here we have a plan for future work, which we are working on right now. Here on the left side, you can see the part described in this paper. And now here, all the right side is what we plan to develop. For example, we want to have a mission service to store all these mission data so that the user can retrieve past missions and analyze them after the mission is already done. Then a drone log for storing data received from the drones while they are being employed for inspections. Then message broker communicating with the drone simulator and managing receiving, for example, telemetry data or images. Then if the drone is deployed for inspection and it collects images while inspecting, we can use those images, put it in an object storage and use them maybe for 3D reconstruction. We can reconstruct the bridge, and then based on the reconstruction, we can develop a 3D mission planning and then send it to the drones. Why we see huge benefits in this drone to cloud interaction is because as drones have limited energy, we want to kind of offload all the heavy computations from the drone or onboard computer and do it where we have the resources, which is inside the cloud. Here we also have services for analyzing images and storing inspection results. Here we can include the weather and maybe avoid planning routes if it's raining or if the weather is not suitable for flight. And that would be it from my side. Thank you very much for your attention.